Okay, hi everybody. We have some questions to answer today. We want to make sure that we are prepared for our test. So we are going to go ahead and see if we can answer some of our questions about, as you can see, the Alkenes test from 2015. So here we go. We want to explain how the bromine molecule is able to act as an electrophile. In other words, an electron attractor. So if we have a bromine, and let's say that our bromine has, let me make sure I can write on my screen. Let's say that our bromine is going to undergo homolytic fission. So one electron is going to go back to each Br. So what we're going to make is a bromine. We're going to make two of them bromine free radicals. And so what those free radicals are looking for, bromine free radical is looking for another electron to react with. So that is what you might be looking for. So it's only looking for one electron, and that might not be what we want to be able to have as an electrophile, an electron attractor. So what if instead the bromine breaks apart heterolytically and both electrons go to one Br, and so we end up with a bromine that is more electropositive and a bromine that by far has already attracted all of its electrons, so it is more negative. So it is this bromine right here that is attractive electrons because of its positive charge. So explain how a bromine molecule is able to attract as an electrophile. It undergoes heterolytic fission. If it undergoes homolytic fission, it might not be able to break that pi bond, but that positive right there is going to act as an electrophile. In other words, an electron attractor. Okay, so the next thing we're going to do is name the product formed when but2-ene reacts with bromine and then reacts with hydrogen bromide. Okay, so we want to be able to figure this out, and but2-ene looks like this. I have a CH3 bonded to a CH, which is double bonded to another CH, which is bonded to a CH3, just like that. And so I'm going to have that first react with bromine, and by bromine we mean Br2. So let's say that they do react through heterolytic fission, and the one bromine ends up with a positive charge. It's going to attract those two electrons, and so we're going to end up with a CH3 followed by a CH, and the Br will jump on one side where the two electrons are, leaving the other side open for the two electrons that the Br ion has, and so we'll end up with CH, Br, and CH3. Okay, and we have to name this thing, so we're going to have to name that as 2, 3, dash, not comma, dash, dibromo, butane, because it is no longer a butene. Okay, so what about if we are adding hydrogen bromide to the mix? What about if we do that? Well, adding hydrogen bromide to the mix means that we are going to break this apart into a bromine that is already got all of its electrons, and a hydrogen that is your electrophile. So there's that happening there, and so we're going to add it to the double bond, so we're going to end up with CH3, and one side's going to get the H and one side's going to get the Br, and it's not going to matter since this is a symmetrical molecule, so it's not going to matter which side gets which, and so we're going to end up with this, and we would call this 2-bromobutane. Okay, so there is our first part. So when it's asking how something can act as an electrophile, you need to be able to discuss how it becomes positively charged, so it attracts those electrons. All right, here we go. Okay, alkenes are commercially and economically important for a family of organic compounds. The reaction of alkenes with bromine water provides a test for unsaturation in the laboratory. Describe the color change that when bromine water is added to chloroethene. So when bromine water is added to chloroethene, the orange bromine water will turn clear, or you could say it will decolorize. All right. Now, deduce the Lewis structure of chloroethene and identify the formula of the repeating unit. So here is our chloroethene. There's our chlorine right there. There's our double bond. And there is our CH2 there. So there's our chloroethene, and it's going to break apart into its repeating unit of CH, Cl, and CH2 with the other arm sticking out here. There is our repeating unit right there. And so where are the 2 points? Point number 1 is right here, and point number 2 is right here for your purposes there. Okay. Explain why monomers are often gases or volatile liquids, but polymers are often solids. Monomers are very small, are small carbon chains. So they have low London dispersion forces, but polymers are long carbon chains, so they have much higher London dispersion forces. Okay, that's what that is right there. Okay, alkenes are an example of a homologous series. State the name of the alkene shown. So you see the key there, and we need to name this. This is where our alkene is right here, and the double bond. And so we have a methyl group attached to the carbon chain that includes. So here's our carbon chain that includes the double bond, and the methyl group is on the second carbon. So this is 2-methyl. -2 propene. Okay, easy peasy on that one. Pretty easy to name something like that. Hopefully you guys find it that easy now. Bromine water can be used to distinguish between alkanes and alkenes. They really like this sort of question. Describe the color change observed when the alkene shown is added to bromine water. It will simply put decolorize, just like we have already talked about. Okay, identify or draw the structural formula and state the name of the product formed. So what we had before was this CH2 double bond to CH, which had a methyl group attached right here, and that was single bonded to CH3. That's what we have, and we're going to add some Br to it. So we're going to be breaking this double bond here. And so breaking that double bond means we're going to add a bromine onto each side of the double bond. So we're going to end up with CH2 with a Br attached here, single bonded to a CH. 1, 2, 3, yep. With a Br attached here and a, is that right? 1, 2, yep. 1, 2, 3, 4. So there's no CH here. I'm so sorry. No CH here. And then we have a CH3 here and a CH3 here. So what are we going to call this thing? We would end up having to call it 1, 2 dash dibromo dash 2 dash methyl and propane would be our ending, because we have the 3 carbon chain right there. Okay, so that was a lot for that one there. All right, so state the name of the product and identify the type of reaction which occurs when between 1 propene and hydrogen chloride. Okay, so all of the types of reactions are always going to be addition reactions. Okay, so if we have addition reactions and we've got one propene, so I'm just going to write it out. Here's my 1 propene. There's my 1-propene, and we're going to add to it some hydrogen chloride. And I know the problem didn't tell us to do this, but it helps me a lot to be able to do this. These two are going to break apart, and so we're going to end up with CH. And we have to figure out where the hydrogen goes now. So the hydrogen has to go onto the carbon that has the greatest ability to spread out the more electronegative. So the chlorine has to go on the carbon, which has the greater abilities to spread out the charge. So we're going to have CH3 because that's where our hydrogen's going to go. So for those of you that are going, wait, now what? Okay, so here, let's go ahead. We still had our CH2 here. And here's going to be where we add the hydrogen on. And then we only have a single bond remaining, and we have this CH sitting here, but this is our secondary carbocation, so this is going to be where our chlorine goes, and we will have this thing here. So we are using Markovnikov's rule for this, and we have to state the name of this product. So the name of this product is going to be 2-chloropropane. Okay. All right. Okay, so the question on this one is asking what organic product is going to be formed in the following reaction. And if you remember, what we form is we are going to be adding water to this. This is showing us that water is the reactant right here. This thing right here is the catalyst. So we are not going to worry about the H2SO4. What we really have here is a HOH here. And we have a symmetrical molecule. So it's not going to matter which side we put the H. It's not going to matter what side we put the OH. So one side is going to get the H. It's not going to matter which side. And the other side is going to get the OH. So there's that. And so we need to pick the one in which that has happened. So if I look at this one, I have CH3, CH2, but it has a 2 there. And that is this part right here becoming a CH2. So that is correct. And then I have the OH on the CH followed by CH2, CH3. That's going to be our correct answer. This next one doesn't have any OH in it as all. That's why we can't use that one. And this one is adding the catalyst instead of adding the OH. So that's wrong. And this one is putting the OH at the very, very end when it should not be. It should be in the middle right here. So that one is wrong. A was our correct answer there. Okay, this next one, predict and explain the structures of the major and minor products when hydrogen bromide is added to 2-methyl-butene. Okay, so there is 2-methyl-butene, and we have hydrogen bromide being added. And so what we have is two highly asymmetric things. So just so that we can see what this looks like, I'm going to go ahead and draw it out. I have a CH3 here. I have a CH3 here, and then I have a double bond to a CH and a CH3 like this. That's what we have. And we are going to be adding HBr to it. So one side is going to get the Br and the other side is going to get the H. And we have to figure out, well, which side is the more stable side to give it to. So the side, remember what we have to determine is the more stable is the one that is the tertiary instead of the secondary. So this carbon right here, that is our secondary carbocation, and then this is our tertiary carbocation. So that means the tertiary one's going to get the more electronegative bromine, and the secondary one is going to get the hydrogen. So if we are talking major and minor, the major product is the one that follows Markovnikov's rule. The minor product is the one that does not follow Markovnikov's rule. So so what we have here is the Br on this one is going to go on the CH3, and I'm going to have to draw it all out again, CH3, C, and then this becomes the Br, CBr, which is now single bonded to the CH, which now has the extra H attached to it, followed by the CH3. Okay, so that's our major product there. Our minor product is going to be the one where that happens oppositely. So we would end up with CH3, CH3. We would have this becoming the CH, and this becoming the CH with the BR over here, and then the CH3, and this would be our minor product. And here's where you have to explain, predict and explain the structures of the major and minor products. So we've predicted the structures of the major and minor products. Now we have to explain the major product is formed because this allows the positive carbocation to delocalize the positive charge over more carbons. All right, and so that's going to be your reasoning why, to be able to explain what is happening. And this is specifically talking about Markovnikov's rule. Okay, so we'll continue on here. Then it says, which monomer would be used to form a polymer with the following repeating units? So this is asking you to undo this. And so what you're going to do is put this and this back in the middle between the two carbons. So we're going to get that double bond back here. So you should end up with a CH2 double bonded to a CHCl, just like that. And there it is, the CH2 double bonded to the CHCl. So you have to be very careful there about putting it back together. Okay. Here is our following reaction scheme. We've got a pentane. It looks like a pentene, actually. The reason why I can tell this is a pentene is because this follows the CnH2n format. So that's why I think that's a pentene. And then it tells you W has the structure of, that's what the structure looks like. And we can have an X and a Y when we add a Br to it. In other words, we're going to have two possible products here when we add the X and the Y to it. And then we're going to come out with Z at the end here. And Z, this Z part might not be what we have learned anything about yet, but we're going to answer the parts that we can answer. So this is asking, give the structure of the geometrical isomer of W. So when it's asking for geometric isomer, it's referring to, oh, this one has the two carbon groups on the same side, so this is the cis isomer. This one wants us to give the trans isomer, so we will end up with CH3H here, and then we would change the position of the C2CH3 to over here, and that's going to give us the trans structure of the geometrical isomer there. So those are isomers of each other. Okay, explain why W has a geometric isomer. And why does it have a geometric isomer? Because alkenes do not rotate around the double bond so two different structures are possible. All right, so there's that. And that's basically what that's getting to. All right, so then we go on. State the full name of W. So now we have to go back and name W, and we're going to name it using the cis part of things. So we have cis dash, and we want to be able to name this correctly. So this is cis dash, and this is going to be, it doesn't have any extra things added to it. So the long carbon chain is a pentene. So this is going to be cis, and the double bond of the pentene is located on the second carbon. So this should be cis 2 pentene. There you go. And so you get 1 point for the cis part, and you get 1 point for the 2 pentene part. State the name of the reaction mechanism by which W is converted to X and Y. And so we would be able to say, you'd be able to say halogenation, and you would have to say also addition. So make sure that you get addition into it, because I really think it's addition they're looking for, but this specifically was the result of adding the HBr onto it to get the Br only in one place. Okay, so if you're wondering, wait, now what? So let's go back and let's look at the idea here that there would be only one Br added. That one Br being able to be added means that we were adding the HBr, not the Br2. If we had added Br2, then there would be another H missing here, and there would be a 2 Brs right here. All right, let's go on from here. Okay, let's see here. Write equations using curly arrows to represent the movement of the electron pairs to show the mechanism in the reaction. All right, so what they mean by this is that they want you to show how the electrons are moving. So if we have CH3 bonded to CH, which is double bonded. That wasn't a CH3, was it? That was an H right there. And that's bonded to a CH2 and 2. That should be a CH, CH2, CH. Boy, I can't do this right. Well, let's try that again. And that then is bonded to, there was an H down here and a CH2CH3. And that means that I have incorrectly shown an H here, which should not be here. So if that's what we have to do, then what that's going to react with then is the HBr. And it is the HBr where the electrons are moving here, and that means that this H is going to be attracted to those electrons right there. And so basically what you then end up having is the CH3 and the H here bonded to now a CH with a single bond here and a CH here, but oops, H here. And this now has a Br attached to it, and then it has the CH2, CH3. And that's a giant mess right there, but it's basically this CH3, CH2, and that's now where the single bond is, and that's got the CHBr on it, followed by CH2, CH3. So where did they want the curly arrows? They wanted the curly arrows here showing the breaking of the pi bond and the adding of the hydrogen on. And so then which one do we decide the Br goes on? And I'm wondering, 1, 2, 3, 4, 5, 1, 2, 3. And I'm looking at this going, there should not be an H here as well. Yep. So then we have, if that's the case, then we have a secondary carbocation here, and we have a secondary carbocation here. So this is only one product. So there is no Markovnikov's rule going on here. Only one product is being formed. Okay. Let's go on. Markovnikov's rule is sometimes useful in predicting the major product in this type of reaction. Explain why this rule cannot be used to predict whether X or Y would be the major product. And the answer is because the carbons in the double bond are both secondary carbons, so they are symmetrical. Okay, so the secondary carbons, and they're both symmetrical, need to be the part of the reaction or the answer there. All right, we are on number 10. Hydrochloric acid is reacted with large pieces of calcium carbonate. Now, this is an example of what some of the reaction rate questions are going to be about. And in previous years, we've gotten to this before this test. We're not going to get this on this test, so you're not going to see reaction rates on this test. But I will go ahead and answer these couple questions here about reaction rates. So let's take a look at. It says large pieces of calcium carbonate. The reaction is then repeated using calcium carbonate powder. How does this change affect the activation energy and the collision frequency? And so the answer, if you remember anything about activation energy, is that activation energy does not change. You would have to change the reaction or provide a catalyst to change the activation energy. So that means that the increasing of the activation energy does not work there because of this. So then we have to say that the collision frequency would increase because we have a powder instead of a large piece. So B would be our correct answer here. But please know that this kind of thing is not going to be on our test. Okay, so then we go to which statement is true about using sulfuric acid as a catalyst in the following reaction? So here is our reaction, and we've got sulfuric acid. It just, like I said, this is another one that will not be on our test, but I do want to go back over it just to say hi to this kind of question. Remember that a catalyst does increase the rate of the reaction. It does lower the activation energy for the reaction, and the catalyst has not been consumed at the end. It is actually remade at the end. So the only two correct answers would have been 1 and 2 only. Don't worry, we will get to these things after we take this test. So onward we go. Which of the following statements about alkenes is not correct? They do have reactive double bonds. That is correct. They can form addition polymers. Yes, that is correct. They do not react by substitution. That's going to be our not correct answer. And they can react with water to form alcohols. That one's correct as well. So C is our correct answer there as the not correct thing. I know that that's completely confusing, and I find it confusing as well. All right. This next part is about the percent composition by mass of a hydrocarbon, and there is and this kind of thing you will see on here, so I do want to take the time to go over this with you so that we can make sure that we understand how to do this. So the first thing we're going to do is recognize that we are doing a empirical formula calculation. So I have 85.7 grams of carbon, and I'm going to divide that by 12.01, and I have 14.3 grams of hydrogen, and I'm going to divide that by 1.01, and I'm going to determine that my moles are. Okay, so what we've just determined is that the empirical formula of the hydrocarbon is CH2. And so yay for us, we've been able to determine that is the case, making sure that we divide by the molar mass and then divide by the lowest moles, and we get CH2 from that. Okay, so then we are going to go on to, now I have a 1 gram sample of the hydrocarbon at a temperature of 273 Kelvin and a pressure of 101.5 pascals, which is the same as 1 atmosphere, and it has a volume of 0.399 decimeters cubed. For those of us going, what? That's liters, everybody. And so what we're going to do is calculate the molar mass of the hydrocarbon, and this is a gas loss question, so we're going to use PV equals nRT. And so the first thing we're going to do is we're going to solve for N using PV over RT. And so we're going to need to be able to use our volume of 0.399 times our pressure, which is 101 times 10 to the 5. That is the same as saying 101 kPa. So just keep that in mind. That is usually what we use for our pressure. So we're going to use 101 kPa. And we're then going to divide it by the R constant, which is 8.314. And that's going to get multiplied by our Kelvin, which is 273. Okay, so this gives us a number of moles of 0.0178 moles. Okay, so if we know that this is that, then we know that grams over molar mass is equal to moles. So that means that molar mass is going to be equal to grams, which was given as 1.00 gram, divided by the number of moles, 0.0178. So 1 divided by 0.0178 is going to give me 56.2 as my molar mass, grams per mole. Okay, so I have determined the molar mass, and now what I need to do is plug it back into the problem. I bet they're going to ask me what the molecular formula is. So let's go see what the next question is. So the next question is deduce the molecular formula. So I've got 56.2. And my original empirical formula is CH2, and we're going to divide that by the empirical formula mass, which is 12 plus 2 equals 14. So 14, 56.2 divided by 14, and that's going to give me 4.01. So that means that 4 times CH2 is going to give me C4H8. That is my molecular formula. Now, it says if this molecule has a double bond between the second and third carbon and it reacts with water, write the equation for this reaction showing the structure of the hydrocarbon, conditions of the problem, the organic product, and the name of the organic product. Okay, so if that's all the case, and we know that's C4H8, then what we actually have is CH3, CH, double bond to another CH, followed by CH3. There is our structure of the hydrocarbon. Got that part done. We are going to make it react with some water, so like this. And the conditions of the problem mean that we have to show it reacting with an acid catalyst. So we've got the conditions of the problem. And now we're going to show the organic product. So the organic product is going to be CH3, CH2, CH, and then we'll have a OH coming off of the end of it or on the bottom of it, and then this one is going to be the CH3 on the end. And so we're going to name this as 2, and this is going to be butane, but it's an acid, so it's butanol, 2-butanol. Okay, so that is our answer to that sort of question as well. All right. Are we at the end? Oh, not quite. Okay. So then this last question, it says 100 centimeters cubed of ethene, C2H4, is burned in 400 centimeters cubed of oxygen, producing carbon dioxide and some liquid water. Some oxygen remains unreacted. So write the equation for the complete combustion of ethene. So here we go. So here is ethene, C2H4, plus some oxygen is yielding some carbon dioxide and some water. And we are going to have to balance this thing. So I'm going to end up with needing to have a 2 here, and I'm going to need a 2 here. So right now I need a total of 6 oxygens. So I need a 3 here. All right, so calculate the volume of carbon dioxide produced and the volume of oxygen remaining. Okay, so I have 100 centimeters cubed of ethene and 400 centimeters cubed of oxygen. And if you remember Avogadro's law, you remember that these can be converted using the mole ratio. So I have 100 centimeters cubed of C2H4, and I'm going to use my mole ratio, which is a 1 to... I want to know volume of carbon dioxide, 1 to 2 ratio. So that way, using that one as my limiting reactant, I would get 200 centimeters cubed of CO2. If I use the other one, 400 centimeters cubed of oxygen, I would have, and it's already told me I have oxygen remaining, so that means that I would have 3 to 2 here, and I would end up with 800 divided by 3, and so that's going to be 267 centimeters cubed. So this is going to be my amount of CO2. So I need to do one more reaction to figure out, or one more calculation to figure out how much oxygen is used up. So 100 centimeters cubed of C2H2 is going to react with the oxygen in a 1 to 3 ratio. So it's going to use up 300 centimeters cubed of O2. So that means that 100 centimeters cubed of O2 will remain. And that's going to be my answer to that question right there. Okay, everybody, I think we've actually gotten to the end of this, but let's just check and make sure that we have actually gotten all the way down here. Yep, that's all there is. Okay, everybody, good luck. I'll see you soon.